In this video, we're going to look at two questions on the topic of capacitors. So first of all, it says a capacitor is made of two parallel conducting plates of area A and initial separation D. It is attached to a constant voltage supply V. And then the energy stored in a capacitor at this state is E1. The separation of states is gradually reduced to D over 3. The supply is then disconnected, and the separation of plates is gradually restored to the value D, where the energy stored is now E3. And the question wants to calculate the difference in the energy stored in capacitor between the final E3 and the initial E1 states. So first of all, I'm going to try to express E1 and then express E3 in terms of E1, and then try to get a difference. And I suppose in this question, difference should be expressed in terms of the variables A, D, V, and D. Okay, so let's start with capacitance. In this case, let's say C1, because the capacitance would change throughout the question. C1 at the first state is equal to epsilon A over D, and yeah. And then let's express E1. So E1 will be equal to a half CV squared, and in this case, that will be a half times epsilon A over D times V squared. Yes, okay, so that will be epsilon A V squared over 2D. And then it says the separation of plates is gradually reduced to D over 3. So basically the capacitance is changed. Let's see, let's say it's C2. Now in terms of C2, the distance reduced by 3, so therefore the equation is divided by the distance, so that will be 3 epsilon A over D. And so therefore, let's say E2 will be equal to basically exactly the same thing as E1 but multiplied by 3, so that will be this. Okay, so and then it says the supply is disconnected and separation plates gradually restored to the value D. Okay, so the major difference right now is that the supply is disconnected. So let's see, if the supply is disconnected, there won't be any supply of current. I'm not sure whether the voltage will actually remain fixed, but I suppose the charge stored in capacitor would remain the same. And yeah, maybe we can calculate from this point of view. Okay, so okay, let's see. See where is the problem exactly. So what we know is that capacitor, the energy stored in capacitor, can be expressed in the format 1 over 2 CV squared. Okay, and I'm not sure whether V will actually change. So I suppose the voltage will change, and then the capacitance will change. However, we can measure the change of the capacitance, so we can keep C. And what we know is that the charge will be fixed. So we need to express the energy stored in capacitor in terms of the capacitance and the charge stored. Right, so for capacitance, what we know is that is equal to Q over V. So therefore we can express V as Q over C. And then if we put this back into this equation, that will be Q squared over C squared, and then the C cancels out, so therefore that will be 1 over 2 Q squared over C. And that will be a format. Okay, so we can apply this equation to the change from the second condition to the third condition. Okay, so let's see. Now we need to express E2 in terms of this equation. That will be a half times Q squared. We're going to take out the C. So what we express here, that will be reciprocal of it will be 3 epsilon A, okay? And that will be equal to dq squared over 6 epsilon A. Now let's express E3. So E3 will be essentially D will be divided by 3. No, the D, because it's stored to initial D, so therefore we can basically just time E2 by 3, and that will be dq squared over 2 epsilon A. Now, how do we calculate the difference between E3 and E1? Okay, so from the question, essentially the final answer that we want to get is in terms of AD, and V. And so basically, if we actually leave Q, it won't be an answer. So I suppose we have to convert this format back into like the voltage format. And my idea is that we can do this. Okay, so basically from these two equations, this equation and this equation, what we'll discover is that E2 is equal to 3E1, right? And then from these two equations, what we know is that, let's see, that will be E2, 3E2 is equal to E3. And if we connect it, so therefore the difference in E will be equal to E3 minus E1. And then what we know is that E3 is equal to 3E2. And then 3E2 will be equal to 9E1. So therefore, it will be 9E1 minus E1. And that will be 8E1. And we just have to do this. We time this formula by 8. And that will be the difference in the energy. Okay, so the final difference in energy will be equal to times 8, that will be 4 epsilon A V squared over D. And that will be the answer to the question. Now let's see the second question. So over here it says, a leaky capacitor is one which does not have a perfectly insulating dielectric layer between the plates upon which the charge is stored. Okay, so it is basically a capacitor with a dielectric material in between, and such a capacitor contains a dielectric material filling the space between the plates, and with an effective resistivity of 1.5 times 10 to the power 12 omega ohms meters. Okay, so the dielectric material actually have resistance, and then the area is given as this, and then there's also the thickness, which I suppose that is the distance between the plates. And then the capacitor is charged from 24 voltage supply connecting in series with 4.7 mega ohm resistor. And okay, so over here, the first part of the question wants us to calculate the maximum charge that can be accumulated in one of the capacitor plates. And so for a parallel plate capacitor C, and then gave us the formula for a capacitance. Okay, so let's see. When is there a maximum accumulation of charge? So, okay. When a capacitor is charged, basically when it's connected to the battery, then the charge stored in a capacitor through time, it will increase like this, because essentially the battery will continue to supply current, and then until the voltage of the capacitor is equal to the voltage of the battery, and that is when the system reaches an equilibrium. So my idea is that it is when the capacitor has a maximum voltage, and that is essentially when the voltage of the capacitor is equal to 24V. Okay, so now we know the voltage, and then we can calculate capacitance. Then we can just directly calculate the charge stored. Okay, so first of all, C is equal to epsilon A over D. And over here, in the question, it's given that the area is equal to 0.603 times the epsilon, the permittivity of free space, that will be 8.85 times 10 to the power of negative 12 over the distance, and that is given as 0.8 micrometers, so that will be times 10 to the power of minus 6. And if we calculate this will be equal to 0.603 times minus 12 over 0.82 minus 6, and that will be equal to, let's say 6.508 times 10 to the power of, that is minus 6, and farads. And what we know, C is equal to Q over V, so therefore Q will be equal to capacitance, which we just calculated, times the voltage, and that will be 24. And this is equal to, that will be amps times 24. And that is 1.562 times 10 to the minus 4 columns. And that will be the answer to the first part of the question. Now let's see question B. So if the capacitor is disconnected from the circuit, calculate the time taken for capacitor to lose half its maximum charge. Okay, so let's see. This is part A. Part A. Now part B. So this is essentially a process of which it's basically a discharging process for a capacitor. Now in this case, the graph will look something like this. So it will gradually decrease like this, and then the equation for it is that Q is equal to Q0 times e to the power of 1 over RCT. So what we want to calculate is the time taken for when half of the charge is left. Time taken loses half its maximum charge. So essentially, basically Q over Q 0 is equal to a half. Now if we apply this to the equation, that will be a half is equal to e to the power of minus 1 over RCT. Now let's see. There's R, there's C, and what we want to calculate is T. We already calculate C. Now the thing we need to calculate is R, essentially the resistance. And what you need to differentiate over here is that it is disconnected from the circuit. So the only resistance arises from the dielectric material that is between the capacitor plates, and it's given as this. We are given the resistivities. Okay, so from the resistivity, we need to calculate the resistance. So that will be L over A, and in this case, okay. the resistivity is 1.5 times 10 to the minus 12, no, times 10 to the 12. And then the length, that will be 0.8482, and the area will be 0.603. Yeah, okay. So the length is 10 to the minus 6 as in micrometers, and then down there we have 0.603. So therefore the resistance will be equal to 10 to the 12, 1.5 times 10 to the 12 times 0.85 minus 6, and down there we have 0.603. And that will be equal to, let's see, 2.04 times 10 to the power of 6 ohms. And therefore, we apply this back to the equation. So it is equal to e to the power of minus, I'm not going to substitute in the values first. So isolate t first. That will be ln and then times minus RC. So t will be equal to ln 1 over 2 times minus RC. And then we can calculate it. So t will be equal to natural log 0.5 and then times minus 2.04 10 to the 6 times the capacitance. Capacitance is over here. That will be 10 to the minus 6, and that will be equal to 9.202 seconds, and that will be the answer to the question.